In this video, we are going to look at the introduction to atomic physics. Now, under atomic physics, you will just focus on the subtopic for radioactivity. Now, how do you define radioactivity? So, radioactivity is just the emission of radiation by a substance. Now, under this subtopic, we'll look at the three types of nuclear radiation, where we'll have the alpha, beta, and gamma radiation. Now, the radiation is just the emission of energy, especially high energy from a moving particle. Now, let's look at some of the properties and characteristics that summarizes the three radiation. So we are going to use a table to summarize these properties. So the first one, we'll look at the type of radiation. Now the first type of radiation is the alpha. We'll have beta and gamma. Then for the second row, we'll look at the symbol for each radiation. So alpha has a symbol like small letter A. Then for beta, it has a symbol like B, or you may use small letter E for electron. Then for gamma, it has a symbol like Y. From there, we'll look at the consist of. So this time we are looking at what the alpha consists of, beta and gamma. So for the alpha, it consists of 2 protons and 2 neutrons. Then for beta, there is only 1 electron per particle. Then for gamma, it's just an electromagnetic wave. That's why gamma is found on electromagnetic spectrum. Now, after we look at what it consists of, we'll look at notation. Now, notation is the symbol that shows that what the radiation or what the particle element has emitted. For instance, if we want to show that an element has emitted alpha, what symbol are we supposed to write? So we use the symbol, the atom for helium, where we have the mass number 4 and the atomic number 2. So I'll explain what these two numbers means. Now for the mass number is coming by just adding the number of protons and the number of neutrons. So that is for mass number. Then for beta has a notation of E, 0, -1. Then for gamma, there is none, since it is just a wave. From there, let's look at the mass. Now for the mass, we'll just compare which one has the largest mass. So alpha, the mass is large. For beta, we have small mass. Then for gamma, no mass. Why? It's a wave. Then from the mass, we move on to relative charge. So for alpha, the charge is positive. Then for beta, it's -1. Then for gamma, no charge. It's a wave. That's the reason. Then from the relative charge, we can also look at the approximate speed. So the speed of alpha is 1/10. 1/10 speed of light. So what does this mean? So this means that the speed of light, we know that is 3 times 10 raised to the power 8, and according to electromagnetic spectrum, under the properties, we say that all electromagnetic waves travel at the same speed of light. So if we multiply 1 over 10 with the speed of light times 3 times 10 raised to the power 8, we'll see that we are going to have 3 times 10 raised to the power 7. So this is the speed of the alpha. Now let's move on for beta. Beta is 9 over 10 to speed of light. So we can see that here beta travel faster than alpha. Now what of gamma? Gamma is an electromagnetic wave, so this one has the same speed as the light, so it's the speed of light here. Then from there we can also look at the ionizing effect. So ionizing effect, we are looking at what happens if we let this radiation enters our body. So the results plus what happens to the body system. So for alpha, the ionizing effect is strong. Then for beta, it's weak. Then for gamma, very weak. Then from there we can also look at can be stopped by. So here we look at the substances in which alpha, beta and gamma cannot pass through. So let's look at alpha. Alpha cannot pass through a paper, then cloth, human skin, etc. Then we can move on to beta. Beta here we will look at a thin metal such as aluminium. Then for gamma, gamma can be stopped by very thick lead, a concrete made of lead. Then we can also look at deflection. So deflection, we are looking at the charges and the North Pole and the South Pole. Now for alpha, alpha can be deflected toward the negative terminal. Why? Because the alpha is positive, it can be deflected toward the positive, negative terminal, since we have opposite charges and we are expecting to have the force of attraction. So it's the negative terminal or South Pole if we are looking at the magnet. Then for beta, beta has a charge of minus, so this one can be deflected toward the positive terminal in terms of electric field. Then in terms of the magnets, we have North Pole. Then for gamma, we said here there is no charge, so here we are going to have no deflection. So maybe let's try to have a picture, especially on deflection. So what does this simply means in terms of the diagram? So let's say we have a terminal here. This is a positive terminal. Then we have another terminal here, which is a negative terminal. and we have here, we'll consider this one as the source of radiations. Now we'll consider the one in white as the beta. Now if we allow beta to move in this direction, so upon reaching here, it is going to be attracted toward the what? Positive terminal. Why? Because beta has a negative terminal. So if we look at let's look at now for alpha. Alpha has a negative, has a positive terminal, so it is going to be deflected toward the negative terminal. Then for gamma, we can say gamma is neutral, so the gamma will just pass through the center of the two terminals. So this is what we meant by deflection. So the positive will be deflected to a negative. Then the one with neutral will not deflect to any, since it's neutral. So sometimes you may have you may encounter the question like you have been given letters maybe A, B, C. Then you are given a question like identify the three radiations represented by the letters. So you just have to look at the deflection and also the charges. So if the charges, for instance, the charges are not given here, you only given the charge for the terminal. So remember that whenever you have a positive terminal, you just have to know that this radiation deflected toward this positive terminal must have the charge negative, opposite to this terminal, which is negative. And you can just remember, what radiation has the negative terminal. So this is our beta terminal, radiation. Then for B, we can see that it did not deflect. So this is giving us the key for gamma. Then for this one, if we look at the nature of the charge for the terminal is negative, so this must be positive. So we can now find out that this is an alpha particle or radiation. Then in terms of the magnets, if you are not given in terms of the positive charges, this should be the north pole, then this should be the south pole. So the point is the beta will be deflected toward the north pole, while the alpha toward the south pole, if magnets are used instead of terminals. So that is what we meant by deflection. Now, away from the deflection, let's look at some of radioactive decay. Now, if you look at radioactive decay, this is just the disintegration of a nucleus due to alpha, beta, or gamma radiation. So what this means is, if for instance we have element X, then with a mass number of A, atomic number of Z, remember the mass number is just the total number of protons and the neutrons found in the nucleus of an atom. So here we have number of protons plus the number of neutrons. So this is the mass number. So now the point is, we are saying what happens if element X emits, let's say, alpha or beta. So we'll look at now the actual example, but we are trying to have some picture. So here, what happens if this element emits one of the two radiation? So you need to know that there are some changes, and those changes will make this X to produce a new element Y. We'll say Y with this mass number of A and Z, then plus here we need to indicate the notation. If it's alpha, we need to indicate the notation for alpha. We said you use the atom for the helium, where the mass number is 4 and the atomic number is 2. But if it is for the beta, we use this E0 and the minus here. Now, after we know the basics of this radiation, the first atom here, this atom is known as the parent atom, because it is the atom that underwent the process of radioactive decay. Then the one produced is known as a daughter atom or nuclide. Then from there, we also have to look at what process has caused the parent atom to change into the daughter nuclide. So this is what we call the transmutation. So this is just the changing of one element into another by radioactive decay. Now let's begin with the alpha. So alpha decay. So we'll look at what happens to the parent atom when it emits the alpha. So the nuclear equation is, if we have element X with the same mass number of A, then the atomic number of Z, then if this element emits the alpha, we are supposed to subtract 4 from the mass number and 2 from the atomic number. Therefore, will give us a new atom Y, which is the daughter, plus the notation He 4 and 2. So this is what it means. So this 4 represents that you subtract from 4 from the mass number, then 2 from the atomic number. So let's look at the example for this. So let's say we have uranium with the mass number of 238, then the atomic number of 92. And if the question is, we need to find the daughter atom that will be produced if this element emits an alpha particle or decays by alpha particle. So what we are going to do is we need to subtract 4 from the mass number. So 238 minus 4, we get 234. So the mass number is 234. Then the atomic number, you subtract 2. So 92 minus 2 is 90. Then here we have 90. Now, if you want to now find the actual name for the daughter atom that has been formed, you need to use the periodic table. Then from the periodic table, you need to just look at the element on the periodic table with the atomic number of 90. Don't worry about whether the mass number that we have is not corresponding with the mass number that you see with the element on the periodic table. So the key point is you just have to look at the atomic number. So on the periodic table, which element has the atomic number of 90? So according to my periodic table, I have thorium. So thorium, Th plus C, we write our H4 and 2. So this is the nuclear equation for this one. Okay, now, so to summarize for alpha decay, if an element emits alpha decay, the mass number reduces by 4 units, while the atomic number reduces by 2 units. Then the other thing that you need to know is the atom produced will be 2 places earlier in the periodic table compared to the original atom. Okay, now let's look at the beta particle or beta decay. So for beta decay, the nuclear equation, if we have the atom X with the mass number A and Z, for beta you just have to know that the mass number does not change, then the atomic number increases by 1, then it will give us this new daughter nuclide plus the notation for beta, which is 0, mass number 0, then the atomic key minus 1. So let's say we have carbon 14. So carbon has the mass number of 14, then the atomic number of 7, of 6. So now the question is, what daughter nuclide will be formed if this carbon atom emits a beta particle? Remember, for mass number, we are saying the mass number does not change, so our 14 will not change. Then for the atomic number, is 7. Then if we look at the periodic table, the element with the atomic number of 7 is nitrogen, plus, then we put our A 0, then minus 1. Now what this simply means is the parent atom here is carbon, then our daughter atom here is nitrogen, since it was the one that was formed during the transmutation. Then the other thing is, you can see that these numbers should be equal to this number. So if you add 14 plus 0, we still get 14. If you also add these two numbers, must be equal to 6. We know that 7 minus 1 will give us 6. So this is the notation for beta decay. Now let's try to maybe analyze what has happened here. Let's find the number of neutrons for carbon. So we said neutrons is equal to the mass number, so in our case 14, minus the atomic number 6. So if we subtract 14 minus 6, we have 80. So there are 80 neutrons. There are 8 neutrons for the carbon atom. Now let's look at what of the number of neutrons for the daughter. So neutrons is equal to, the mass number is still 14 minus 7. So we'll see that the neutrons is equal to 7. So if we are doing the beta decay, we can see that the number of neutrons decreases, because in the atom of the carbon there were 80 neutrons, while from the calculation according to the daughter atom, we can see that we have 7 neutrons of this nitrogen. So what has happened to 1 neutron? So what this means is that neutron has split into a proton and an electron. That's why we can see that the electron, the number of protons has increased, and we have this electron here. So that is what it means if we try to analyze what has happened. So that's it for this video. I just wanted to give you some insight about radioactive decay, and if you find this lesson interesting, please feel free to write in the comment section below so that I can make more of these. So that's it for this video. Thanks for watching.